Hello and welcome. Today we're going to be talking about matrix inverses. Okay, so let's put this in perspective. We've talked about inverses before, so let's talk about inverses for real numbers. So recall from a previous video where we were talking about real number algebra, and if you have some sort of x, some sort of, well, actually let's talk about, we have an a, and it's an element of the real numbers, all right? The question then is there a, what we call A inverse, such that A inverse times A is equal to 1. Okay, and the idea here is that, of course, the answer then is pretty straightforward. If A is not equal to 0, if it's any other real number except for 0, then 1 over A is A inverse. And then that certainly works out that 1 over A times A is equal to 1. Okay, and again, remember 1 is that special number. It's called the multiplicative identity. Okay, so it's the multiplicative identity. It's the one number that if you take 1 times A, you get back A for every real number. Okay, and here we have this thing now. Every real number has an inverse except for 0. Okay, so that works out really well, but now we want to ask again, what about matrices? Okay, so if I have a matrix, and we're going to restrict ourselves to square matrices. So again, we're talking about n by n matrices, all right? Is there a matrix such that, so we want to, the question then is there a matrix such that, and I'm going to call this matrix I, such that I times any other matrix, and this will be an n by n matrix. We're always going to be considering square matrices. I times that matrix is just A again. Okay, so basically I behaves like 1, 1 for real numbers. So it turns out I is a special name. I is called the identity matrix. Okay, just like we have 1 as the multiplicative identity, this I is the multiplicative identity for n by n matrices. And it has a special form. It's actually equal to. It has 1s down the diagonal, and here's that for 5 by 5. Oops, I need to draw my lines a little clearer. Just make sure not to, like that, and then that goes down there. There we go. And then there's zeros everywhere else on the off diagonals. All right. So this is for 5 by 5. All right. So of course, for other for other dimensions, of course, you just have fewer entries. So basically, diagonal of 1s. And that's what makes a identity matrix. So let's try out this identity matrix to see that it truly does have this property. I should also note that it is a matrix that does commute. So I multiplied on either side will always equal the other matrix. All right, so let's give an example here. Let's talk about an example. I'll take A. We'll just do a 2 by 2 case now. So we'll say this is going to be 1, 2, 3, 4. There's a matrix. And my identity matrix in this case, again, is going to be 1s on the diagonal, and then on the off diagonals, zeros. All right, so I'm going to multiply this on this side. 1, 0, 0, 1 times 1, 2, 3, 4. And a good way to identify it is if I take that column and I multiply the entries in that column by the respective entries in the top row, that leads to the top corner, the 1, 1 position there. And clearly we see we get a 1 out of it. All right. Likely if I take this same column here, this column 1, and I multiply it by the second row, I'm going to get the first column, second row of the result matrix. And that, of course, is going to be 3. Now if I go to the second column here, and I multiply it by that top row, I'm going to get a 2. And then I multiply this by the bottom row, and I get a 4. And of course, this is exactly A again. So check. Might as well do it the other way, just to make sure this works. And we can clearly see by doing the multiplication that we're going to get 1, 2, 3, 4 out of it again. So check, that works as well. So that's a good example to show you how it works. You could try other examples, but the idea here is that I, the identity matrix, is a very special matrix that whenever you multiply it by another square matrix, you always get back out that same square matrix. Okay, so that's nice. So let's now back up. We have this nice idea of an identity matrix. Let's now talk about it again, the multiplicative identity in use. We want to find again, we have the multiplicative identity 1 was that special number that results when I multiply an inverse of a number times itself. So you can actually think of 1 as being the defining value where a times its inverse is equal to 1. Right, the question then is, that begs the question for matrices, is there a matrix, what we're going to call A inverse, such that when I multiply A inverse times A, I get out the identity matrix. Of course, you see that's exactly the statement there, now just written in this way. And it turns out this question is, the answer to this question is sometimes. So let's, the first case, of course, is what if A is the 0 matrix, right? So it's equal to 0, 0, 0, 0. Well, clearly, we know in this case A inverse can't exist. And it's clear that once you multiply 0 by any, I'll call it, maybe we'll talk about a different matrix. If I multiply the 0 matrix by B, I always get back out the 0 matrix, all right? So there's no way to understand, if I were able to, I have to find a way that would produce B again. And there's no way to do it. Multiplying by 0, of course, you can't come back from that. Okay, so clearly 0 doesn't have an inverse, just like it did for the real numbers. So let's now, but it turns out there's other matrices. So there are, so this is a fact, there are many matrices that don't have inverses. Okay, so that's a fact. So and we're going to encounter a few later on, and we're also going to. So that leads to another questions: how do we compute A inverse? And how do we determine when it exists? So those are two, those are two. That's sort of a two-part question. We can call that 1 and 2. And the question then, we'll get to that in a second. So now let's just work out an example and kind of see, again, what we're talking about here. So let's do one quick example. We're going to start with a linear system. 1, -1 is the top row, and -2, 2 is the bottom row. Or sorry, -1, 2 is the bottom row. We're going to have a set of unknowns, x1, x2. And I'll just say 3, 2 is the result. So I'm going to call this matrix here, that will be A, and this vector is X, and this vector here is B. All right, so the idea is so the goal is to solve for X, right? That's the unknown. So the technique we use is to use Gaussian elimination. All right, so and we could do that, but I'm not going to do that right now. Another also is to find, or instead of doing Gaussian elimination, we could find A inverse. And then what we do then, of course, is if here's our if we had AX equals B, and these are vectors, and then I multiplied both sides by A inverse. I'll give myself a little bit more space there. If I multiply by A inverse, okay, like that, and then of course what I can do is I can use the associative property of multiplication of matrices to compute this, and this by definition was A inverse times A was by definition going to be the matrix that creates an I there, all right? And of course that equals the identity times anything is equal to the thing itself. And then all we'd have to do is multiply this matrix by this vector together to find X. Of course, that achieves our goal. Right, so the question then is, of course, how do we compute A inverse? And how do we know it exists? All right, so we know the basic framework here. So what we're going to do, of course, is we're going to use Gaussian elimination. But we're going to be a little bit more careful about how we use Gaussian elimination. And we're going to actually identify one more fact. Okay, and that fact is that row operations can be represented as matrix multiplications. Okay, so this fact that row operations, and which are the things that create that make up Gaussian elimination, we can actually, instead of doing the row operations on the augmented matrix, we can represent that same thing in terms of matrix multiplications. So let's get to that. Let's write down our problem again. We have 1 negative 2, 1 negative 1, negative 1 2, and I have x1 x2, and that's going to be equal to 3 2. All right. So what we want to do now is I'm really not worried. This is my B, so I'm going to put that aside for a while and really just focus on this matrix here and doing the row operations on it. So that's my A. I'm going to bring it down here. And what I'm going to do then, of course, is start doing my row operations. So I see here that if I add row 1 to row 2, that can create my new row 2. And that gets me the 0 I want. So 1, negative 1, 0, 1. That's my first row operation. Right now, put up here, now, let's see if we can represent row 1 plus row 2 goes to my new row 2 as a multiplication. So it turns out, let's try this. And this is going to be called my row operation matrix. I'm going to give this a special name. I'm going to call this operation 1 because it's the first operation we did. Okay? And we're going to multiply it by our starting matrix, our A, just this one right here, right? So I want to find what to define here for this operation matrix, it actually represents this activity. Okay, so the first off thing we want to do is we're actually going to leave the columns alone, right? So I want this to be, I want this matrix here to represent this operation so that the product of A times this operation matrix results in this result here. So I'm going to write that result down because that's what I want to come out of this thing. All I'm doing is recasting my row operations in terms of a matrix multiplication. The first thing I see is, of course, the top row stays the same. And so, in fact, I'm going to take that top row of the identity matrix, and that's going to produce that same top row here. The next thing I need to do is now realize that what I'm really doing is I'm adding the two rows together, and that's making my new row 2. So I actually want to take one row 1 and then one row 2 and add them together. And we can clearly see when we multiply those together, well, maybe I don't need to do that, but if I multiply these two by this top row, I get a 1 there. And then when I go to the next row, I can see that it really truly is adding the two rows together, and I result in that 0. Now when I go to the next column here, I multiply the top row and I get the result I need. The top row stays the same, but the bottom row, of course, I'm summing the two, and I get that same answer there. Okay, good. All right, now the next step then is I want to do, I see clearly my result. The next thing I want to do in terms of my similarity transformation is I need to add row 2 to row 1 to put my matrix in reduced row echelon form. So I do that. So I'm going to take row 1 plus row 2 and make that the new row 1. And that becomes then 1, 1, 0, 0. And this, of course, is in reduced row echelon form. Okay, and we're done. So the next thing I want to do now is I want to do the same action then and multiply the two. So now I want to keep row 1 the same. So what I do is now I multiply. I'm going to put a blank matrix there, and that's going to be my O2, my next row operation. I'm going to take this result here, put it in that spot right there, 1, negative 1, 0, 1. And now I want to multiply. I want to find something to put in here so that I get this result. Okay, so we can do that. And again, what we do, we want the row 2 to be the same, so I simply put that part of the identity matrix in that part. And of course, I want to add the two rows to get the top row here. So what I do is I put a 1 and a 1 there, and that makes the summation. Okay, so we do this, and you can check that that actually works. But now let's back up here a bit. Right, remember, what we did was we actually did two matrix multiplications. So really what we did was, in summary, RREF was achieved by multiplication by O1 then O2 on A. So let's write that out. So again, this was all multiplication from the left. So this is O1, or so that was our O2 there, and there was O1 here. And then we had A here. Okay, and that will be now, we can write it out. I see O2 is sitting right here. So 1, 1, 0, 1. And then we have a O1 was right here. So that's a 1, 0, 1, 1. And then finally, we put A itself there. That will be 1, negative 1, negative 1, 2. And that was equal to, drum roll, the identity matrix, the reduced row echelon form. Okay, we can clearly see then that that implies that I can do all these multiplications in any order, right? So what I did was, of course, we multiplied these two together, took the result, and then multiplied them together again. So this right here, this matrix was O1 times A, right? So instead I can do the associative law and say that that is actually going to be the product of these two matrices together. That is going to be A inverse, because that's precisely what we wanted. We wanted the matrix times A equal to the identity. So it turns out then that A inverse is going to be equal to the product of these two matrices. 1, 1, 0, 1 times 1, 1, 0, 1 in that configuration. All right, so let's now go to the next page and see if we can summarize this. So again, what we had was A inverse. I'm going to write out the whole problem again. A was equal to 1, negative 1, negative 1, 2. And then A inverse was going to be equal to O2 times O1, which was, let's write it out again. I'm forgetting my, so we had 1, 1, 0, 1, and then we had 1, 0, 1, 1. Okay, so let's actually write that out all the way. Let's do this product here. We'd see if I multiply that and this column by that row, and we get 2. And this one we get 1 on the second row there. We get 1, and then finally 1. So this, I contend, is A inverse. So let's check. So if I put 2, 1, 1, 1, right, that's A inverse times A, 1, negative 1, negative 2, negative 1, 2. And we can write that out. Did I do this correctly? I think I made a mistake. Oh, never mind. I see my error. Everything is okay. All right, so I multiply 2, and I multiply that by negative 1, and I get 1. Good. All right, and then I multiply down here by this column here, by that row, and I get 0. Now I multiply this column here by that one there, and I get 0. Multiply this column by that row, and I get 1. All right, and that, of course, is the identity as desired. I can now check the other way. 1, negative 1, negative 1, 2. That's my A. And then put the A inverse 2, 1, 1, 1. A inverse. And that will be equal to, and you can check this, 1, 1, and the zeros on the off diagonal. So, and that's one important fact here, that A inverse does commute with A. However, in general, matrices do not commute. AB does not necessarily equal to BA in general. But it is true with A and A inverse. They form a special pair that does actually equal the identity no matter which order you do them in. And that's another statement then, of course, is that A inverse, if I take its inverse, I get A again, right? And that's the important point here, is that the inverse of an inverse is the matrix itself. Right. So now we know where the inverse comes from. So basically, let's write down the punchline here is that inverses are obtained by row operations. So everything you did with row operations, nothing has really changed. We're still doing the same procedure. We're just dressing up the row operations through these row operation matrices. And we're able to achieve the result by defining this new quantity. But it's still row operations that achieve the result. It's just a new notation that helps us understand it. So the final question then is, okay, this seems a little clumsy. finding these O2 and O1 matrices, if you have to do many row operations, you can imagine that could be very onerous, that it's not really going to be helpful. So let's see now, let's define a formal procedure to find A inverse. Okay. So one thing we can do, obviously, is what we do is actually augment A with I. Okay. So what we do here is we're writing A and putting that in a matrix, put a little dotted line down there and put I right there. So let's look at this example here. We'll look at an example. We'll try this one. 1, 2, 2, 1. All right, so that's a different matrix. So what I'm going to do now is do exactly that. I'm going to go 1, 2, 2, 1, and then a 1, 1, 0 on the off diagonal. Okay, so 1's on the diagonal. All right, so now what I'm going to do then, of course, so what I'm going to do is, just like I do before, is I'm going to find O1, O2, O3, all those row operations. But then when I multiply, O1 but I multiply O1, O2, and O3 to A and the identity sitting next to it. So the idea here is, of course, what we do if we multiply O1 by A and the identity, and there's some distributive property that goes in there, and what we get then is A times O, back up there a little bit, O1 times A, dotted line, O1, and then I go to the next step, O2 times O1 times A times O1, and that becomes equal to O2 times O1 times A, dotted line, O2, O1, right? And we can continue that all the way until you get the identity over there. We found all of them. And then we'll have ON, ON minus 1, all the way to O2, and then O1. And this, of course, then reads out the identity matrix. All right. And so we can see that, but now we don't actually have to find, so we can just do row operations. You don't actually have to find the row operation matrices, just do row operations. But the idea is basically the I on the right, i.e. this identity matrix, collects all row ops that form A inverse. All right, so let's let's now just clear this page off. Okay, so I'm gonna clear that off, and now let's see if we can do this. We had this 1, 2, 2, 1. That was our matrix. What I'm going to do is, again, augment that with 1, 1 on the diagonals, and then zeros on the off diagonals. And now I'm going to find its inverse. And what I'm going to do is do the normal thing we do with row operations. So again, this is going to be similar to, I'm going to take row 1 is going to stay the same. Now row 1 times -2 plus row 2, that's going to be my new row 2. And by design, top row stays the same. Bottom row gets a 0 in that lower left entry, and we'll get, that becomes -4 plus 3, or sorry, -4 plus 1 becomes a -3. and we get a -2 in that entry of row 2, and a 1 there. Okay, so we see now that this right there is exactly O1, that first row operation matrix. The next thing we got to do now is now figure out what to do to zero out this entry. So the first thing we can do is actually divide. We'll take row 2, divide it by -3 to get a new row 2. So we're just doing a straight multiplication of rows. And then we get a 0, we get a 1 there, and then we get a positive 2/3, and we get a -1/3 there. All right, so we're getting close here now. One more row operation. We're going to take row 2 times -2 plus row 1, and that's going to be my new row 1. We write that out. 1, it's going to be 0 by design, and now we're in reduced row echelon form. And then we need to now multiply -4/3 is adding to 1 is going to give us a -1/3. Like that. And now a negative or a positive 2/3 plus 0, we get a positive 2/3 up there and a -1/3 there. Okay, so this is now O2 times O1, and actually I guess O2 and that's O3. I'll call this O2 times O1, right? And this whole thing here then is A inverse. All right, and so we can actually check that. We can see here there's a common factor of 1/3 that sits out in front of everything. So what we can do is go 1, 2, 2, 1. I'm going to multiply it now. I'm going to stick that 1/3 out and times it by 1, 2. So that's a -1 there, and a positive 2 and a -1 there. And then there's that 1/3, and I can actually stick that out front and deal with these two matrices. So all I'm doing here is checking. Yep, and seeing what we get out of this. So we're going to get we have a -1 and a positive, so that yields us a 1/3. And the result here, you'll see there's a 3 in that corner, and then there's a 0 there, a 3 there, and a 0 there. And of course, we divide by 1/3. We get a 1, 1, 0, 0, which is equal to the identity. So this seems to work. We're doing really well. So the only last question we have then is, and we're going to have to address this in another video fully, is like what happens, or what the final question we had is was actually not what, but when. When does A inverse not exist? And the answer is pretty simple. It's when row reduction to reduce row echelon form does not yield the identity matrix. So we saw here, after doing all the row operations, we actually yielded the identity matrix. But when we cannot do this, when the row operations lead to some other form of reduced row echelon matrix, then we say that A inverse doesn't exist. All right. So thank you very much. And in a later video, we'll do more examples of finding inverses this way.